It's all right. Might be nice up here in the room with a big periodic table. Be amazing. All right, so we got to come with a balanced equation, right? So we're going to take the diborane, B2H6. We're going to react it with hydrogen, or I'm sorry, sodium hydride. So that's going to be sodium. This is something kind of unusual. In this case, we have hydrogen being a -1 charge. Those are hydrides. And what we're going to end up getting is we're going to get sodium borohydride. We get then NaBH4. Oh, now we got to balance this. What are we going to do with that? So if I put a 2 there, right? If I can put a 2 there, it gets me 8, right? And I think I can put a 2 there. Does that seem balanced? I think it's when you go to balance equations before 8 o'clock. What? Yeah. Yeah, I know. It's like cruel and unusual punishment, isn't it? I think that's right, correct? So we have 2 borons, 8 hydrogens, 2 sodiums, now 2 sodiums. That seems balanced, correct? Now, a big clue, huge clue. This is your clue, right? How do you start a problem? If they give us the amount of each starting material, we know we have to do stoichiometry. How many times? Twice. All right, go ahead. You go ahead. If you want, you can start with the sodium hydride, and then you can go to the diborane. You guys need a periodic table? Yeah.
Two up front, does it all find all of them are just sodium?
This is all of them. I think there's two molecules of sodium diboron. So you have two of those molecules. Here are the two molecules of sodium hydride.
Okay. Thank you.
Yep, two molecules with two moles of that.
Please.
Got the sodium hydride, then you can start working with the diborane then. Ready? Got it? Okay, so we're gonna start with the 7.89 grams of sodium hydride. So then we're gonna go grams of sodium hydride to moles of sodium hydride, and then moles of sodium borohydrate, and then ultimately to grams of sodium borohydrate. That makes sense? That's the pattern we're gonna go. We have 7.89 grams. Sodium sodium hydride. Convert that into moles, correct? 24 grams. Now we're gonna look at the mole ratio here. We have 2 to 2. We have 2 moles. NaH to 2 moles. Sodium borohydrate. And that's what, 37? What you got? All right. We go through these units, we'll cancel. So now we're in the units of grams of sodium borohydrate. 7.89. 7 was divided by 4. And for this, I got 12.16 grams sodium borohydrate. Is that good? That's up close to that. From the ball, yeah.
Somehow it seems all my numbers got like twice the size of yours. I don't know, why did I go multiplying the two in, or was I not supposed to?
I don't know why you would do that, because remember, this is why you want to be consistent. 1 mole of sodium borohydrate is 37 grams, right? So you want to, that comes from the periodic table. The twos are from the balanced equation, right? So you always want to, remember, this is from the, some of you say, can we put 2 and 2 here? So I don't know why you want to do it, just, I'm always consistent. This is what I get from the periodic table. The periodic table tells me this is what the moles of 1 sodium borohydrate is. So I'll always have 1 mole down here, always. Yeah.
I'm confused on like the 1 mole of the sodium hydride, because I was wondering why.
Here?
Yeah, I was wondering why it was 2.
Because this is the mass of 1 mole of sodium borohydrate. Sodium hydrate. So this, remember, this number and that number come from the periodic table. And if it comes from a periodic table, that is going to be the mass of just 1 mole of that. The twos are for the balanced equation.
Okay.
That makes sense?
First voice session to tell us how many moles.
How many moles? Yes. So if I'm gonna make this, I need 2 moles of that. And that's where I put it in this step. That makes sense? So these 2 steps always come from the periodic table. Since they come from the periodic table, it's always going to be 1 mole. Because that's what the units on the periodic table are. Make sense?
It's always 1.
Yeah, always. Yeah, always, because that is the mass, excuse me. When you look at the periodic table, the units on all those numbers are gram per mole. So they're always going to be the 1 mole of that. This is where you incorporate the coefficients out in front. Make sense? Is that good? Good. Now we're going to do the next one. Now we're going to look at the 8.16 grams diborane, and we're going to do the exact same thing. So we have 8.16 grams diborane. Now I'm going to say 1 mole of diborane is what, 26? So we got 26 grams E2H6. Right, linkage boron is 10 and hydrogen's 1. Now I look at the mole ratio. I have for every 1 mole of diborane, I have 2 moles of sodium borohydrate. So 1 mole diborane, 1 mole sodium borohydrate. And 1 mole sodium borohydrate is going to be now 37 grams of sodium borohydrate. Now, if we cancel our units out. Oh, wait, oops, I made a mistake. This should be 2, shouldn't it? Yeah, 2. Got ahead of myself, sorry. All right. That will cancel, that will cancel, 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 cancel. There we go. All right, so units cancel out. 8.16. Times 2 times 6. So in this case, I got 26 point, oops, sorry, 23. 23.2 grams. What you got? Close enough. 8.16 times 2 times 37, is that divided by 6? Yeah, close enough. Yeah. All right, so which one's gonna be our limiting reagent?
Top one.
Top one, exactly, because that's where we get this, that's where we produce the small amount. This is also going to be our theoretical yield, that's exactly right. That's gonna be our theoretical yield. Now. Done with that. Now it says, if we're gonna assume 88.5% yield, how many grams of sodium borohydrate can be prepared? So our percent yield. Remember, is equal to the theoretical. Divided by the actual. Oh my goodness. Time is too stinking early. Actual was theoretical. 500, correct? So now we know that our yield, right, is going to be 0.885 is equal to our actual, that's what we're looking for, divided by our theoretical, right? And that's going to be actual divided by our theoretical is now going to be 12.16 grams. It's our actual. Six times 5. We can. This is going to be our percent year. We can come up with 10.67 grams sodium borohydrate. 76, about 10.76. So we're in that ballpark range. Good. Great. We'll get to this one in a little bit because it has to deal with molarity. We haven't talked about molarity yet. Like I said, I just redid these slides this summer. All right, now we're gonna do empirical molecular formulas. We did these in lab. Half of us did these in lab yesterday. This is where we're actually calculating either an empirical or molecular formula. Now, molecular formula is the one that we're most comfortable with, right? That's the one where it's the actual numbers of the atoms that make up the the compound, the substance. The empirical is just nothing more than a molar ratio of what of those compounds. So, for example, if we look at a sugar, for something like glucose, we would have C6H12O6. That would be the molecular. We looked at CH2O. That would be the empirical. So the molecular formula is going to contain the actual number of atoms in a molecule. The empirical formula is simply just going to be the relative numbers. Okay. So if we're just, for example, if we're looking at a sugar C6H12O6, that's going to be a molecular formula for a sugar. The empirical formula would be CH2O. Right. You ever want to hurt your brain, go study carbohydrate chemistry. It is very difficult chemistry. All right. Okay, so we're gonna calculate some of these. Now, the one thing I should say, in order for us to calculate the molecular formula, the only way we can calculate this is we have to be given the molar mass. If we're not given the molar mass, we can't calculate this, all right? The first thing we're gonna calculate is gonna be the empirical formula, right? So that's the first thing. The first thing we're gonna calculate will be the empirical formula, then we'll calculate the molecular formula only if the molar mass is given to us. If the molar mass is given to us, we can't calculate this. It's impossible. Right? So styrene is a compound used to make styrofoam cups and insulation. It's going to contain 92.3% carbon and 7.7% hydrogen by mass. And its molecular weight or molar mass is going to be 104 grams per mole. So since we've been given the molar mass, we can calculate the molecular formula. Now, some of you may do this differently than how in high school than how I've done it or at other schools. You don't have to solve this problem the same way I solved the problem. Does that make sense? There's other ways of solving this. This is just how I solve it. All right. I've had several students say, we didn't do that in high school. Can I solve it this way? Yeah, by all means, go ahead. The first thing I do is I write all the percentages. So 92.3, and then this is going to be 7.7. Now, if I assume 100-gram sample, right? If I assume 100-gram sample, then these percentages become grams of that substance. Does that make sense? So I automatically assume 100-gram sample. Right? If I assume 100-gram sample, then I'm going to convert to moles. So I'm going to convert this to moles. So carbon is 1 mole of carbon is 12.01 grams of carbon. This becomes 7.8, 7.68. 5. So far, so good? Yeah.
You always assume that it's 100-gram sample?
Yeah, always. Because the nice thing is, this is where I differ from some people. Some people, there's multiple ways of doing this. I always assume 100-gram sample so that my percentages automatically turn into. So if I have a 100-gram sample, then I know that sample, 92.3 grams of that sample is carbon. So that's why I do that. Yeah.
You just basically cancel out the grams of carbon and then just put 92.3 on top.
Yes, yeah, yeah. So you could just same thing as what we did before, right? Just lazy this morning. Good. Do the same thing with hydrogen. Sorry, I always remember hydrogen is 1.008 because that's how I was taught. If you just put 1, that's good enough. It doesn't have to be. So 1.7 divided by 1.008. In this case, we get now 7.64 moles of hydrogen. Okay. Now this one's kind of neat because we have basically the same molar mass, but then the next thing I do is I divide by the smallest number of moles. So I divide by the smallest number of moles. And the goal of that is I want to get, what I'm basically doing is I'm going to set up a ratio between, in this case, carbon and hydrogen. All right. So I'm going to divide by my hydrogen because that's the smallest, but we can see that this is essentially going to be 1 we have 7.685 moles of carbon. I divide that by 7.64 moles of hydrogen, and I'm essentially going to get one, right? 7.685 divided by 7. In this case, we get 1.0006. We can say that that's close enough to being just one. Right? So what does that tell us? What does this tell us? What it tells us is for every 1 mole of carbon, I have 1 mole of hydrogen, exactly. Or for every 1 atom of hydrogen, I have 1 atom of, or for every 1 atom of carbon, I have 1 atom of hydrogen. That's exactly right. Yeah. So now, once we do all the dividing, we can write now the empirical formula. We come up with the empirical formula. And what that's going to be is, in this case, it'll be C1H1. I'm just writing it that way just because we know for every 1 atom or 1 mole of carbon, we have 1 atom or 1 mole of hydrogen. So that now becomes our empirical formula. So we're almost done. Does that make sense? Now we want to find the molecular formula. So we'll determine the molar mass of the empirical formula and in our case, that's going to equal 13 grams, right? It's going to be 13 grams per mole. 1 carbon, 1 hydrogen. Well, now we're going to divide the given molar mass by that of the empirical formula. So it's going to be 104 grams per mole divided by 13 grams per mole. Right? So that gives us 8. What does that mean? What that means then is that the empirical formula is 1/8 the size of the molecular formula. So now, if we want to get the molecular formula, yep. We take 8, what we get here, times C1H1, so we get now C8H8. And that's our molecular formula, and that's our empirical formula. Does that make sense? Yeah.
So for example, 104, how did you get that?
That came right from here. So, and that, Karen, that's a good question. That's got to be given to you. If this is not given to you, you can't do the molecular formula. This has to be given to you. If it's not, you can only do the empirical formula. You can't do anything more than that. Yeah, good question. That's, I had to get it from there. Otherwise, you'd have no idea what it could be anything. You just wouldn't know. All right. Pretty easy. They're not, they're really kind of fun. They're just a little time consuming and tedious. They're not bad. All right. So I'll let you do one. This is ibuprofen. Determining empirical molecular formulas of ibuprofen, a headache remedy. It contains 75.69% carbon, 8.80% hydrogen, and 15.51% oxygen by mass. So since this gives us a molar mass of 206 grams per mole, we know we can find the molecular formula. We know we can do that. Read this. I'll give you a few minutes to.
Is it pretty safe when we always divide by the smaller in chemistry? Just to,
In this case, you want to do it because that way you can get an integer. You don't have to deal with decimals. So that's why I do that. Some people, to me, it just makes more sense to come up with an integer than it would actually come up with a decimal. But it doesn't, there's no rule you have to do it that way. You can. But if I'm working with an integer, it just seems easier to work with than a decimal. Yeah, it's so.
I get 1.4, but I do say it's one, so you can't round the one up.
For these, for the actual ratio or the moles?
After you get the moles and then you divide
ratio.
ratios.
Just leave as 1.4, right? What we're gonna do some kind of goof with that. We may round it up to 1.5 and maybe multiply the whole thing by 2.
Off.
Does that make sense? We can do stuff like that. The last one was really easy because everything's kind of one to one.
Yeah.
And after you do a couple of these, you kind of get a flavor for how the you can just leave it as that. You just leave it as 1.4. It doesn't have to be, it's just the ratio. Does that make sense? But what we may, I'll show you what we're gonna do. We may multiply the whole thing by 2, all right?
Yeah.
I mean, they're just numbers, right? That's all they are. They're just numbers. You can always kind of tweak them. All right, Zach?
Yeah, that's lost.
Huh?
Lost.
We'll get you unlocked, all right? I promise. Okay.
I just don't know what to do because of it.
The what?
It's 3, so I don't know.
Okay, so divide, you have to do 2 divisions, right?
Oh.
You have to do 2 divisions. So you divide the 2 larger ones by the 1 small ones. Does that make sense?
Yeah.
So you do 2 divisions. All right? Dividing the 2 larger ones by the smaller one. Okay?
So we're gonna be using
Whichever one's the smallest.
we're gonna do that 2 times.
Do it twice.
Okay.
Yep, that's exactly correct. Yeah, yeah.
Wait, what are we doing this? Sorry.
That's fine. You're gonna get 3 moles.
Yeah.
You're gonna divide by the 2 larger ones by the 1 smaller one.
Okay.
At least it's not crazy hot here this morning. So you keep working, I'm just gonna convert this into moles since we know how to do that.
Listen to. This is Brett.
Divide them, or?
No, yeah, once you get them all divided, so everybody got this for the most part?
Yeah.
Okay. Now we're gonna divide by the smallest, right? We're gonna divide by the smallest. The smallest is gonna be the oxygen, correct? So if I take now 6.302 moles of carbon, divide that by 0.969 moles of oxygen. I should give about 6.5. Yeah, about 6.5, correct? Now, if we do the next one, take 8.73 moles of hydrogen divided by 0.969 moles of oxygen. 8.7. divided by 0.969. I get about 9. Does that make sense? Where we're at? So now what that tells me then is my empirical formula. Is gonna be what? C,
7.
we'll go with 6.9, right? Or 6.5, right? Our hydrogen is going to be what? 9, and then O. If we multiply by 2, that turns into 13.
Rewriting the one then?
If you want to, it's no big deal. We can write one, so that's fine. Now, let's say you don't like decimals. You know, I need decimals. How can we get rid of this decimal? Multiply by 2, right? So if we multiply this by 2, we get C13H18O2. Right? Now, if you calculate the molecular weight of this, the molar mass of this is equal to 206 grams per mole. What was given to us in the problem? 206. So not only is this the empirical formula, it's also what? Molecular formula. That makes sense? So that's why I think you want to be. What? So if you get it, for example, let's say you get this to be 0.33 or 1.33, then what would you want to multiply it by? 3, does that make sense? That makes sense? Yeah.
How would I see 13 no also?
Because when I calculate the molar mass of this, I got 206, which is what it tells us is the molar mass of the problem.
So if we had done a smaller, molar mass of the C13H18 or total, would we have just still multiply the number in after getting the?
So yeah, what if you'd have calculated the more mass of this, Vinny, so let's say you call this the empirical form, which is perfectly fine, you could have done that, you would have gotten 103. You'd have taken that, you'd have taken the more mass that they gave you, divide by the 103, so I'm half as big as what I should be, so I need to multiply by 2. I knew I wanted to multiply this by 2 because of the 0.5. I knew if I multiplied this by 2, that's gonna get me a whole number of answers. That makes sense? If I were to get 1.333, then I know this would want to be 3. Yeah. right.
So to get the 206, we just added carbon.
Yeah, the 12 carbons, 13 carbons, 18 oxygens, and 18 hydrogens and 2 oxygens. There. So it'd be 12 times 13 plus 18, and this would be 32. Yeah,
So. Divided by 16, I keep getting this. Why is that what it is?
well, I don't know, that doesn't look right. So if I take 15.51 divided by 16, that's what I got. We're good? Okay. All right. Okay, I'll finish this on Friday. Well, what I was going to do now is go over. I always write an outline every time I do a test. Because it just helps me so I know that I don't leave something out. So I'll go over that outline with you. Now,
So helpful.
I am not a very creative human being by any means of imagination. All I do is I just take the titles of my slides and put them on an outline. That's all I do. Yeah,
Is there ever a case where it won't be like 100 gram sample? Like, will it say?
I make that. No, I made that 100-gram sample. I'm always going to make that 100-gram sample because that turns the percentages into grams.
Will there ever be like in the question, it'll say in a.
Oh, yeah, you can do that. Yeah, absolutely. Yeah, absolutely. And then you just take that percent times the amount you're given, and then that will give you the mass of that element. But yeah, very simple. I'm gonna make the math easy, so I'm gonna make a 100-gram sample. Right? Okay. And let's see here. Now this ought to be interesting, but we'll give it a shot. Okay. So chapter 1. And what I try to do, I really try to spread the points throughout all the chapters. Does that make sense? Now, chapter 1, there isn't a whole lot to that. Does that make sense? So that's mostly going to be, I would say the big thing you want to do with that is the conversions. Does that make sense? That's where a lot of points of the conversions are kind of big. But we talked about classification of matter. So it'd be solid, liquid, and gases. Correct? We talked about pure substances. We talked about some pure substances. We also talked about mixtures. We did temperature conversions. I will give you the conversion from Fahrenheit to Celsius or one of those two. Does that make sense? Because for some reason in my mind, I cannot seem to get that stupid thing memorized. I don't know why it is. I should just really sit down and do it. Somebody in my household makes fun of me because I don't do that. Anyway, whatever. And then we just did other conversions. All right. So this is really kind of the highlights of so conversions would be metric to metric, right? Anything English to metric, I will give you that conversion. I don't expect you to memorize any of that. Okay. So that's chapter 1. Chapter 2. We talked about subatomic particles, so the atomic structure. We talked about protons, neutrons, and electrons. Talked about the Millikan oil drop experiment. Okay. You remember what we got from the Millikan oil drop experiment? Remember what important thing we got from that? Yeah, we got the mass to charge ratio of the electron. Yeah, big one was the mass. We got the mass of that. And we did Rutherford's experiment. Remember what that showed? That showed that the atom had a nucleus to it, right? They took some gold foil, bombarded it with alpha particles, which is really the nucleuses of helium atoms. They were bombarding it with something they didn't even recognize, they didn't even know. Then we did isotopes. Then we discussed ions, and then everybody's favorite. This should be a roaring applause. You all should be so happy with this stuff. Nomenclature. I just find it very boring. Sorry, I'm just not being a nomenclature fan. Yeah. And in there we did metal, non-metal. Metal, non-metal. We did non-metal, non-metal. Sorry, make a better door than window. Then we also did polyatomics. Okay. So far, so good. Makes sense. And that's basically chapter 2, chapter 3. Chapter 3. So we dealt with aqueous solutions. Aqueous solutions. We had strong, weak, and non electrolytes. We had the solubility rules, precipitation reactions. Bless you. We had Smith big rounds. Redox reactions. We dealt with some acid-base reactions. It's just these would also be called neutralization reactions. And then we did combustion reactions. In these acids and bases, I talked about strong acids and weak acids, strong bases and weak acids. That's a piece of information. Just kind of keep that in the back of your mind. Does that make sense? We'll review that as we go on. Does that make sense? I'm just saying that for the future. I don't know about you, but I don't like surprises. I really don't. I'm kind of a boring human being. So I always want to tell you where we're going in this class. Does that make sense? Here's why we're doing this. Here's why you're learning this. This is where it's eventually going to go. Does that make sense? I think it's much better if I just tell a story of chemistry as opposed to just throwing a bunch of facts at you. And that's why Chem one's not my favorite, because it seems like all you find folks is, I'm just constantly lobbing facts at you. Does that make sense? I like Chem two much better because I think the story is much more complete. And I love teaching physics because that story is beautiful. So I like teaching stories. Let's see here. We're good? That makes sense? All right. Now, some of the stuff we've not finished in chapter 4, it will be on the exam, but it will not be on the quiz for Friday. Does that make sense? I remember taking quizzes in college and we would talk about something and often there's a quiz on it. I didn't have a chance to really think about it. So in chapter 4. And that's going to be stoichiometry. So here we had the balanced chemical equations. Right, so we balanced chemical equations. We talked about. Actually did this in chapter 2, but it's all kind of the same. Avogadro's number. We did mass percent. We did limiting reagents. We also did percent yield. This is going to be the actual. Theoretical. And then the stuff in blue is what we're going to talk about on Friday. It won't be on this quiz, it will be on the exam. We're going to talk about solutions. Concentrations. And this is going to be molarity, which is equal to the moles of solute over liters of solution. And then lastly, we look at dilution. And that will be M1, V1, M2, V2. And just because I know you're asking for, say, oh, could we do this? Yes, we're going to do some, it's going to be riveting. Solution stoichiometry. We're good? All right. We'll talk about this on Friday. If we don't have time, I'm gonna give you plenty of time to finish the quiz. We can always finish it up on Monday, but we're pretty much done with chapter 4. All right? All right. All right. Have a good Wednesday.